Hi, we are Group 10, and our project was the adjustable grip strength trainer. So we found that most commercial grippers use fixed resistance, which don't really allow precise progression and rely on poor biomechanics that make them ineffective for rehab. So our motivation came from climbing injury experience and the need for rehab tools that increase load gradually and measurably, especially since grip strength is closely tied to mobility and overall health. So our solution is a gripper with an internal spring preload adjusted by a worm gear and a threaded loader, which gives it a smooth, continuous resistance. And it uses ergonomic ABS handles for proper hand alignment, and the self-locking worm gear safely holds the preload during use.
We use several engineering foundations, including spring mechanics such as Hooke's law and worm gear mechanics. We perform stress and deflection analysis and selected materials such as ABS plastic and several different steels. We consider the anthropometrics and ergonomic handle geometry, and we use CAD modeling, GD&T, and planned FEA verification. We assumed that the spring is treated as a linear body, and we simplified the friction and energy losses between the worm gear and rack. Our grip force is treated as uniformly distributed and parallel to the motion of the hand. Our spring is a parallel behavior, and the thread pitch is constant.
For our CAD design, we use SolidWorks for both the design work and the simulations. Our design consisted mostly of ABS plastics with some steel for the worm gear and the spring. Our design provided 2.2 inches for the range of motion when gripping, and our preload mechanism had 15 pounds of preload per 0.1 inches turned. For our design progression, we started with this design on the bottom left with the handle on the outside, and we iterated as seen in these drawings on paper to a design with the handle on the inside instead, which was more secure. And you can see in the top right with our design on handle on the inside.
As you can see in the exploded view, the rack connects the worm gear to the parallel springs, which is attached to the handle, and it's all held together within the frame. The isometric view displays what our final product would look like.
Here we have our bill of materials, and this will have each component. So we have the frame in the bottom right with guide rails to slide the grabbing part. We also have a groove here for our thumb. It's more ergonomic. Here we have the springs, and then this is the handle, also for ergonomics. We made grooves for each finger. This is the worm gear with the shaft and the handle. This will be turned to adjust, like preloading the spring to make it more difficult. And then this worm gear will connect to this rack here, and this is what pulls the spring backwards.
So here are our spring dimensions. We have a K value of 75 pound force per inch using each of these values. Here's our worm gear where we decided that 0.1 inches of stretch in the spring yields 15 pound force through one rotation. And for our outcomes and material choices, the internal load path was stable with the worm gear mechanism, and the low adjustment torque supports the easy user preload tuning. The geometry also effectively distributed the force and reduces stress concentrations, which was verified using the phi analysis under 20 to 200 pound loading. And we selected the given materials for our um, design.
So this video shows the analysis in motion. As you can see, the springs stretch and then counteract the force. On the next slide, we have the devices during the FEA analysis. As you can see, all the springs are taking on all the forces of the stresses and the strains. The next slide will show the worm gear. And once again, the stresses and the strains are mostly concentrated inside the thinnest part of the shaft.
The key results are that we designed a spring load mechanism with variable resistance and a comfortable design. The springs behave linearly as expected with a low adjustment torque needed. For achieved and significance, we incorporated elements from class to CAD and simulate a user-friendly design, and we use the engineering design process to solve limitations in commercial design to make a device safer for rehab progression. And here are our references.